We're in Unit 5. This is Notes 2. Today we're going to take a look at Riemann sums and definite integrals. Riemann sums is a concept that was covered in pre-calculus BC, the end of the year. Maybe one of the last things you did in pre-calc BC. So a lot of this will be a review for you, if you remember it. It's been a little while. So first of all, let's talk about what we're doing with a Riemann sum. So let's say that we have this function, f of x, and we would like to be able to find the area underneath the curve, between the curve and the x-axis from x is equal to a to x is equal to b. So we're looking for this area here. That area we can denote by this. We can denote that area. That's what we're looking for. We can denote it by the integral from x is equal to a to x is equal to b. Those are our boundaries of the function with respect to x. So there is definitely going to be a relation between what we're doing today with Riemann sums and integration. Okay? We will get that very soon, like tomorrow. All right. So, but for today, we're just going to be approximating this area. So we're going to approximate. We can approximate this in different ways. One way to approximate it is with rectangles. I drew these vertical lines for a reason. First of all, I drew them vertical because we're going from x is equal to a to x is equal to b, and it just made sense. But also because I wanted these to resemble rectangles. Okay, so this looks exactly like a rectangle on three sides, but at the top it doesn't look like a rectangle because there's a curve there, right? Each of these tops is some curve. But we can turn these into rectangles. Remember, we're only approximating, so approximating this area. The reason I would like to use a rectangle is because we can very easily find the area of a rectangle by base times height or length times width. So the first one that I like to do is using the left side. The left height is going to be the height of each rectangle. So I'm going to close this rectangle off there, and I can find this height. I'm going to close this rectangle off there, this one here is going to go a little bit above the curve, this one's going to go a little bit above the curve, a little bit above. So some of the rectangles are above the curve, some are below the curve. These last ones are going to be below the curve. So we can approximate this area using the left height of each rectangle as the height, and this is called a left Riemann sum. If we used the right side of each rectangle, it would be a right Riemann sum. I have another kind of a better picture that I drew. So this would be a left Riemann sum, and I did the blue rectangle to show you, so that you can see the left height is the height of the rectangle. That would be a left Riemann sum. Here we have a right Riemann sum, where that same blue rectangle, now we're using the right side as the height of the rectangle. We can also use not the left or the right, but the middle. So the midpoint. So in between each rectangle, use whatever the very middle x value, go up to that height. That would be the height of that rectangle. Which one do you think would yield the best approximation? Probably the midpoint sum, right? Or we don't have to use a rectangle at all. We could, instead of using a rectangle and squaring off these heights, instead of doing that, we could connect each height with a trapezoid. So that is called a trapezoidal sum. So each one would be connected like that, so we'd have a little trapezoid there. For a trapezoid, we need to know the area of a trapezoid, which isn't as easy as length times width or base times height. It's half of the height of the trapezoid, which is going to be our delta x for us. So half of delta x times the sum of the bases. Really what you're doing here is you're taking your base and multiplying it by the average of your two heights. Add the two heights and divide by 2. That would be the average of your two heights, right? That's how I like to remember this. The base times the average of the heights. Very different from the midpoint sum, which is the base times the middle height, period. Not the average of your two heights, just the middle height. Okay? So that's our Riemann sums. Now let's pull out your examples. In this first example, we are given a table of values. It says let f of x be a continuous function. Selected values of f are given in the table above. In part A, we're supposed to estimate the area under f from 0 to 140. So I did give you a little graph of this as well, graph of these points. I gave you the graph of the points just so that you could visualize it. You will, in general, you will not get a graph. You'll just be given the table. Okay? So, in part A, we're going to approximate this integral, approximate the area, using a left Riemann sum and 5 subintervals as designated in the table. Okay? So I'm going to start off with what I'm trying to find. I'm trying to approximate, just approximate. Since we're asked to approximate, I don't want to use an equal to sign because that's not true. We're approximating, so I'm going to use the approximately equal to sign. That's important, you guys. You never want to say something is equal to something it's not equal to. So if we're asked to approximate or estimate, use the appropriate sign. Okay? All right. And we're using the left Riemann sum. So the first change in x will be 20, right? That's our change in x. The first height that we're using is going to be our left-hand height. So it's going to be this 100 here. And that's the first area of the rectangle, base times height. Now we're going to go to our next rectangle. Well, the next rectangle is right here. What's the change in x? The change in x will be 30. The height that we're going to use is the left-hand height, this 90. The next change in x will be 20, and we're using the left-hand height will be 80. The next change in x, delta x, will be 30. The height, we're using the left-hand height will be the 80. And lastly, the last rectangle, the fifth rectangle here, has base length 40, delta x 40. We're using the 90 height. If you're doing a left Riemann sum, you will not use the rightmost height at all. Okay? Now, there is absolutely no reason to simplify this if it's an FRQ. If it's a multiple choice, yeah, go ahead and simplify it. If it's an FRQ, please do not. You have no idea how many times I've had to mark somebody's paper wrong because they chose to go ahead and multiply and add and they made a mistake. If you do multiply and add, you make sure you safe stop here first. If you just can't stand it, then go ahead and do that and multiply and add. I'm not going to. There's no reason to. All right. Part B, estimate the same area using a right Riemann sum. Still 5 subintervals, and now we're going to do a right Riemann sum. We're still approximating, so use the approximately equal to sign. Okay, so for our first rectangle, the delta x is still 20, but now we're going to be using the right-hand side as the height of the rectangle. So I'm going to have 20 for the base length, the delta x. The height is 90, the right-hand height. Your next rectangle has delta x, change in x 30. The right-hand height is 80. Next delta x is 20. Right-hand height is 80. Next change in x is 30. Right-hand height is 90. And then 40 times 130. If you're doing a right Riemann sum, you will not use your leftmost height at all. Okay, part C. Estimate the same area using a trapezoidal sum. Still 5 subintervals. It's important to note how many subintervals they want you to use. Almost always it's like this. So, we're still estimating this area. Now we're going to use a trapezoidal sum. So here's how I think of a trapezoidal sum. The base length, the change in x, times the average of your heights. The average of your heights, 100 plus 90 divided by 2. The average of your heights. And then go to your next trapezoid. The base length is 30. The average of your 2 heights. The next base length is 20. The average of your 2 heights. Next base length is 30. Average of your 2 heights again. And then the last one will be 40 times the average of those 2 heights. And that's it. Okay? So that is left, right, and trapezoidal approximations. Okay? And again, there's no reason to simplify. By the way, if this is an FRQ, AP has got to see these values. They've got to see what you have to write down each of these heights all over the place. So do not, like up here, this 20 times 100, do not just write 2,000 for that, because then AP is losing their ability to track what you're doing there. So you have to write out what I have written here. You have to. Okay? If you wanted to, you could take this a step further, and instead of writing 20, write that as 20 minus 0. Write 30 as 50 minus 20. You could do that. AP doesn't require that. They can see. A lot of times you can subtract this very quickly. So you can just write the 30 for that. But you could, if you wanted to, write 50 minus 20. Okay? Part D. Given that f double prime is greater than 0 on this interval, is the approximation found in Part C an overestimate or an underestimate? Well, let's think about that. If f double prime is positive, that means f is concave up. So that means we have this concave up curve connecting these points. It's concave up all the time. In Part C, we used a trapezoidal sum to approximate the area. Well, if we're concave up, let me draw that down here. If we are concave up, then what is a trapezoid going to give you? The trapezoidal sum is going to be more than the area under this curve. So the trapezoidal sum will give you an overestimate. So here's what I'm going to write. A trapezoidal sum is an overestimate since f double prime is greater than 0. That's all I'm going to say. I'm not going to describe the curve. I'm not going to describe the areas. I'm not going to do anything else because this is all I need. It's all I need. AP will be looking for trapezoidal sum, overestimate, and that condition that makes it true. All right? So, my advice to you is not to write a paper when it comes to giving a reason for an over or an underestimate. Please just be succinct. Okay? Another example. Number 2. All right, let h be a continuous function. Selected values of h are given in the table above. Estimate the integral from 30 to 90. I always make sure if it's 30, they want 30 to 90, I go make sure that I'm using the correct values. So we're using a midpoint sum and 3 subintervals. 3 subintervals for a midpoint sum. It's very common. If you're given a midpoint sum, it's very common to have, you're not going to have 5 subintervals again, or 10, whatever. You're not going to use everything. You can't if they ask you for a midpoint sum. Okay? So, 3 subintervals. So here's my thought process. This is one of my heights. Okay, well this is one of my sides of the rectangle. Okay? The other side, I'm going to have to skip one because that's going to be used for the height of my rectangle, and I'm going to go over here. So these are the sides of the first rectangle. The second rectangle will be here, and the last rectangle will be here. So in other words, you're using the 30 and the 50, but not the 40. You're using the 50 and the 70, but not the 60, the 70 and the 90, but not the 80. Very common for a midpoint sum. Okay? And then you're using the middle number, the middle x value, that 40, as the height. So you're using that as the height of your rectangle. So you're using this as your height. You're not going to use the 5, you're not going to use the 10, only the 7. You're using this middle value as the height of your rectangle. So you're using the 15, not the 10, not the 14. And then lastly, you're using this one as the height, not the 14, not the 20. So a while back I saw a student do this. And I kind of liked it. It made a little bit of sense. Okay? For a midpoint sum, that's what you're going to do. Okay? So I'm writing down what we're approximating. I'm using the appropriate symbol for approximation. Okay? And these are just back to rectangles. So it's just length times width, base times height. The first base length is 20. The first height is 7, base times height, plus next base length is 20. In a midpoint sum, these are all going to be the same. Each base length is going to be the same. The next height is 15. The next one is also 20. Height is 16. Those are my 3 subintervals, my 3 rectangles used to approximate that area. All right. Number 3, approximate this using a left Riemann sum. So this is an example that does not give us a table. However, we could kind of create our own table if we wanted to. We're going to be using a left Riemann sum and 4 equal subintervals. 4 equal subintervals. We're going from 0 to 2. So x is going from 0 to 2 in 4 subintervals, 4 equal subintervals. That means our change in x each time will be a half. It has to be. Okay? So our change in x will always be a half in this problem. So if we're using a left Riemann sum, let me go ahead and start that out. 0 to 2 of this function is approximately equal to the first base length is a half. The second base length will also be a half, as will the third and the fourth. Okay? Now I need the height. What's this height? Well, the height will be the leftmost height, which will be when x is 0, right? So let's just call f of 0, well, I'm going to call this f here. So if I put 0 in for x, I get 0 plus 0 plus 1, that's just 1. So the leftmost height is 1. Then I'm going to go to the next one. The base length is a half. What's the next height? Well, the next height is when x is a half, right? And if we put 1/2 in for x, and if we add fractions and stuff, we're going to get 1.375. Okay? 1.375. I used my calculator on that, clearly. Okay, if we put 1 in for x, this one I can do in my head. If we put 1 in for x, we get -1 plus 2 plus 1, which is 2. So the next height would be 2. And then we have one more to get, and that will be when x is a half higher. So 1 plus a half is 1.5, and if we put that in for x, we get 2.125. So that last height is 2.125. And we do not need to find f of 2 because that we're using a left Riemann sum. That would be the rightmost height, and we don't use that for a left Riemann sum. So this is our answer. Now, FYI, this adds up to, we wouldn't do that, we would stop here and we would be done, okay? But FYI, this is 3.25. And in our calculator, if we actually compute this, we can compute, this is called a definite integral, and we can compute that on our calculator. If we put that into our calculator using math, if I hit the math button, and then I'm going to go down to number 9, math 9, 0 to 2, to 2, negative x cubed, plus 2x squared, plus 1 dx. That's the exact area under that curve. We got 3.25. That's not too bad, is it? Not a bad approximation. All right, number 4. The amount of water in a draining tank is given by a strictly decreasing function. Whenever they give me information like that, I know I'm going to be using it somehow. So I like to bubble it or square it or whatever, note it. So I'm probably going to have to use that somehow. W is given in the table below. Use a right Riemann sum with 4 subintervals to approximate this integral, this definite integral. From 0 to 40, I always make sure, because every once in a while they'll give me an integral that is not my leftmost value or not my rightmost value, but here this is fine. It's all good. Okay, write Riemann Sum. So I'm going to write what I am approximating here. Integral 0 to 40, WT. We are approximating, so I'm using the appropriate, not an equal to, it's approximately equal to. Use the right sign. All right. So a right Riemann sum. The first delta t in this case will be 10. We're using the right hand height, 78.3. The next delta t is 5, right hand height. Next delta t is 10, right hand height. Last delta t is 15, right hand height. And there is absolutely no reason to add those up. None at all. Even if we had a calculator in our hand, don't do it. Say stop. Okay, part B. Is your answer to part A an overestimate or an underestimate of the actual value? All right. Well, this is where we're going to use what they gave us up here. The function is strictly decreasing. That means it's always decreasing. It might be decreasing in concave down. It might be decreasing in concave up. It might be a linear decreasing. Whatever, it's decreasing. It's somehow decreasing. Okay? We used a right Riemann sum. That means if that's the height, the right-hand height, every rectangle is going to be below that decreasing curve. Every rectangle is below it if we use the right-hand height. If we had used a left-hand height, every rectangle would be above it. But with a right-hand height, it's below. So I'm going to say a right Riemann sum on a decreasing function yields an underestimate. And I'm good. Don't describe anything. Don't say, as shown in my picture on the left. Don't say anything like that. Keep it very brief. Right Riemann sum, decreasing function, underestimate. But put it in a logical sentence. Okay? You can't just write those three things and call it good. Explain means to explain, but this is a perfect explanation. All right. So that is our topic of Riemann sums. We're going to continue this topic tomorrow, going a little bit deeper.